change in the order of presenters. Mr. Jenkins pointed this out to me, that in the update, it indicates that we're going to reverse the order of the first two presenters this afternoon. So our first presenter this afternoon is actually Mr. Cornell Jenkins from the Department of Physics. The topic, as you can see, is cascade physics at the CSUDH Hadronic Structure Laboratory, and his faculty mentor is Dr. John Price from physics. So please entertain.
All right, good afternoon, everyone. My name is Cornell Jenkins. I'm a physics major undergraduate, and my mentor is Dr. John Price. Today I'll be speaking about the cascade physics at the CSUDH Hadronic Structure Laboratory. So pretty much to give you guys an overview of what's going on, the main objective is to study the nucleon structure, mainly to understand how protons, the characteristic properties of protons. So what our objective is to look for the missing states to improve the understanding of the excited states. But the problem is the proton structure is getting hard to do because the nucleon states, based off this graph, are broad and overlapping. The black dots are the theoretical, this is the theoretical data, and the red capsticks are the experimental data. So based off the overlapping, it gets pretty difficult to understand which states are which. So to begin, we want to study the structure of the proton. I'm sure you guys all know that the proton is made up of two up quarks and one down quark. So we want to know what the proton is made up of, what the quarks are doing. We want to observe the interactions because we cannot study the protons directly. So what we do is we fire a photon beam at liquid hydrogen, and what happens is, based off the interaction, we can either stretch the states, we can add or subtract the orbital angular momentum. We can also manipulate the spin. So based off the spin down, we can have a spin up, which would turn into a delta particle. Now, the different combinations of the properties, they all have different mass, different decay modes, different spin, and different parity. And to elaborate parity is what my other colleague is going to speak about after I get done. The issues are the excited states of the protons are short-lived. So due to the Heisenberg uncertainty principle, the masses that overlap, all of the masses are pretty much poorly defined based off the picture that I actually just showed you guys previously. So our alternative to what we do is we study the cascades. So to begin with, I will eventually touch on the cascades, but we have the QCD Lagrangian. This thing is pretty massive, but be honest with you guys. But let's just go ahead and attack it. So when we see the L sub naught, this pretty much it makes the particles in the different octets have different mass bases from different excited octets. So, for example, if we have a multiplet where the quarks or the particles are stretching or spinning, this L sub naught pretty much allows each octet to have different masses. Now the L sub m gives all the particles within the octet different masses. So without the L sub m, all the particles in the multiplet would have the same mass. So based off the QCD Lagrangian and the SU3 symmetry, the SU3 symmetry is the strong nuclear interaction which obeys the SU3 symmetry that leads to the multiplex. So based off the arrangement of the different multiplex, the couplet and the octet, we look at the symmetry of which and the Lagrangian, the QCD Lagrangian. So the multiplex are essentially predicted by the symmetry group that we use to describe the nuclear interaction. So, for example, we have, looking at the group theory of things, we have three different quarks. This one, this one, this one. All of which can either have an up, a down, or strange quark. So, based off the group theory, we pretty much get a decouplet, 2 octets, and 1 singlet. Now, looking at this term based off from the QCD Lagrangian, this term actually is the only place where the quark and the quark's mass come in. And once we really look at the structure of how the particles are aligned, the cascades actually are directly related to the neutron and the nucleon. And so the horizontal lines all have the same strangeness right here, and the diagonal lines all share the same charge. And pretty much the same for the structure of the code. Now looking at the multiplex, we assume that, just pretty much to recap everything I just pretty much gave you guys, we assume that we have the multiplex that have the same mass scale set by the different wave functions, spin, and parity. So all the first order of all the particles have the same mass and the spin parity in the different multiplex. In regards to the multiplex mass, part of the mass depends on what the quarks are doing, if they're being stretched, if they're just hanging out, if they're spinning, and the other depends on how they're made up. So when we study the cascades actually have similar properties to the protons, but they're just much heavier. So the philosophy is, and the idea behind our research is, if we can understand what the cascades are doing and the characteristic of the cascades, then it would allow us to understand more about the proton, because the proton decays so much more faster than the cascade. So our plan is, you want to find, well, based off the nucleon state that decays too quickly for us to use, we need a particle that has the properties related to the nucleons and have a much narrower width than the nucleons as well. So using the cascade to study the nucleon, the cascade widths are approximately 9 times narrower than the nucleon. So when we look at this graph over here, taking into account the Heisenberg uncertainty principle, we see that the y-axis is the width and the x-axis is the mass. So let's say, for example, we look at approximately 2,500 MeV, 2,600, something like that. We see that based off the nucleon state, the width is way up here. It's around 650 MeV. But approximately at 2,500, looking at the cascades, the width is down here. So that pretty much allows us to know what exactly is happening in these different excited states from studying the cascades in comparison to studying the nucleon itself. So basically at Dominguez, what we do is we have a kaon and a proton, and we get a kaon plus and a cascade minus. But since there's no good kaon beam available, we pretty much take a different approach. We have a gamma proton, and we get out a kaon plus, and we have a variable. So we study the variable. First, we understand the properties and the characteristics for strangeness and mass and of the kaon plus, and we use the x. We don't directly see the cascades. We actually, using invariant masses, we understand that pretty much that the x, the variable, should be a cascade. So we look at the properties, and that's another way that we're able to observe the properties of the cascade. So all of the cascade plus all the excited cascades, should be accessible via this process. A lot of the experiments are done at the Jefferson Lab, J Lab. I don't really know too much to hit on this, so I'll just pass it by. And these are the older detectors of how we, study the cascades. And here's just another view of it. And basically studying the first results. So we have two independent data sets, and the less background in the G6A set, there's more data in this set. So it's a series of events, and we see, at these different energies where the spikes come from or occur at. Well, that's a way to explain it. So based off what I was previously saying, this is the different plot of what we start with and then what we get. And in conclusion, we want to pretty much extend this approach to look for more cascade states, which would allow us to compare to the nucleon states. Right now, we have about 14 different nucleons and 10 different deltas, but we only have 6 different cascades. So based off the numbers, we're pretty short of cascades. So we need to actually find these because there should be a direct relation of the same amount of nucleons and deltas as to the same amount of cascades. So that's pretty much what the last line said. And that's it. Thank you for your time.